Hi everyone, now we're down to a characteristic of size for our family of stars. And we sized the sun. We found the diameter of the sun, we found the volume of the sun, and we found the mass of the sun as well. But when we look at the universe of stars, we're going to find all different kinds of diameters and masses and densities. So let's look at how we're going to determine how our universe size works for our stars, just as it works for this family here. When we look at the 80 closest stars to our sun, you know that the pattern forms along the main sequence. We've already discussed that. And when we go out and we look at this a little bit more closely, we can look at another part of this beautiful diagram that looks at radii of these stars. So the one radius runs right through our sun. So our sun here is right at the intersection of one radius, meaning the diameter of our sun is the standard by which all others are judged, and the luminosity of our sun is the standard by which all other stars are judged as well. And we have other dashed lines for 1/10 of the sun's radius, and 10 times the sun's radius, and 100 times the sun's radius. And sometimes some stars are 1,000 times the sun's radius as well. But it's a beautiful way to analyze the data for this. When we add on the 100 brightest stars, which are not the closest stars in our universe, things start to really change up quite a bit for this HR diagram. So all of the brighter stars than our sun, all of the 100 brightest stars in the universe are brighter than our sun. And that means that, guess what? All of them have a larger radius than our sun, or the vast majority of them have a larger radius than our sun. And many of them are within the radius of our sun to 10 times the radius of our sun. This area in here is pretty well populated for brightest stars, and they happen to be along the main sequence as well. So they are, many of them are between 1 and 10, and many of them, especially those in the giant areas, are between 10 and 100. This is introducing an area in here called the blue giants. They're called the blue giants because they are in the blue temperature zone in the ultraviolet temperature emission zone. And we also have the red supergiants, and guess what? They are emitting more infrared light. They are emitting more red light. So this is bringing in some different classifications, and of course you know by the Stefan-Boltzmann law that we discuss more, that as a star's temperature increases, its total energy emissions will increase as well. So that when you have an enormous star, it has a higher chance of having a high temperature and more emissions. And in fact, I think I'll change up that slide a bit. The area of the star is really linked to its luminosity. So while we were able to tell its temperature by spectral classification, we can also look at its size and predict something about the temperature as well, because bigger stars can emit more, and they can be more luminous than small stars. And in fact, we have seen that there are giant stars, there are supergiant stars, there are dwarf stars, which have smaller radii than our sun. And so these are some of the supergiant stars that are in the thousands of radii bigger than our sun, like Antares. And you actually looked at Antares in your lab when you looked at parallax for the brightest stars in the sky. So many of you looked at Antares for that. The brightness is due to the amount of energy it's putting out, and it's due to the size, so that you have this very luminous region up here, and you have these very big radii up. Here's a way to show you the scale of Antares versus our sun. Here is Antares and the relative scale compared to our sun, which is right here in this speck right here. So that gives you an idea of the scale of the radii that we're discussing here. And in terms of that, you can also look at this about the power that is coming out of these areas that is dependent on temperature and is dependent on area and radii of these stars. So when we look at the Stefan-Boltzmann law that says that the hotter a star is, the more emissions it will put out, that means that there is a constant, the Stefan-Boltzmann constant right here, that's directly related to temperature. And the total energy produced by the star is related to the area of the star with that Stefan-Boltzmann constant and the temperature. In fact, we can find the size of the star if we know the luminosity of the star and we know the temperature of the star. So there is a proportional relationship there that we can work this and isolate the radii as being proportional to the square root of the luminosity over the temperature to the fourth power. So there's a way for us to directly relate luminosity, temperature, and size. And you've looked at that constant there. It's usually known as that. I'm not good at my Greek letters. Maybe that's omega, which is the Stefan-Boltzmann constant. You don't have to know that constant. You have to know the fact that luminosity, temperature, and size are all related and are all proportional. And in fact, when we look at this radius, sometimes we see that these radii that are very small are actually much less luminescent. That's the white dwarf region that we have here. Small radii and less luminescence. It all goes together. We can come up with the total size. You know this volume of a sphere is 4/3 pi r cubed. So it's all related back to these areas and radii measurements that we're taking. And when we put in the closest 20,000 stars to our sun, we really start to see this red giant region being populated. In terms of that, 90% of the stars on our universe that we know of at this time lie along that main sequence, which is based on luminosity, and 9% of them are really red giants, and only about 1% of them are the white dwarfs, which are small radii and less luminescent. See you on the next one.